Today, this is the second informal talk by Christian Ferko from the UC Davis. He will discuss universal tensor deformations. Please welcome him.
Great. I'll thank Jungi and the other organizers for the invitation to speak. And I now realize that I was very foolish. I thought that I would have to bring my special Hagoromo chalk all the way from the US, and then I arrive here and there's lots of pieces of Hagoromo, so it's not necessary. But good, as Jungi said, I want to give, I'm taking the word informal very literally, so this is going to be an extremely informal talk. This will be a review that I'm hoping is accessible to students or people who have not worked on TT-bar. As a corollary, it means that the experts in the audience will be very bored, so I apologize to Roberto and Jungi and other people who are very expert in TT-bar. But I'd like to give a big picture first about why the usual TT-bar is exciting. And then in order to transition to my second talk later this afternoon, which is much more speculative, in the second part of this talk, I'd like to sort of give a guided exploration to sort of maybe help convince you that the title or the topic of my later talk, this root TT-bar deformation, is something which is not so crazy. It's maybe something that you might have discovered on your own. But okay, first for the review part, let's start at a very high level. So something that I think we all think about is that if you imagine some abstract space of quantum field theories, so I'll draw a sort of blob. And the way that we usually think about this is to organize it into a collection of, say, conformal field theories, which are fixed points of the renormalization group flow. Maybe there's a CFT3 down here. And these different CFTs can be connected both by renormalization group trajectories, which we think of as beginning in some UV theory and adding, say, some relevant operator, which flows down to an IR CFT, which is different from the original one. So we can have a few flows of that form. There may also be marginal flows, which connect a line of conformal field theory. So these are generated by adding some marginal operator, if you like. So maybe some O marginal. There's some O relevant 1 over here, and maybe some O relevant 2 over here, and so on. So this lets us think about the space of quantum field theories in a sort of a mapped out way where we have certain signposts that are conformal field theories and then paths between them that are generated by operators. So this is great. This lets us think about the space of conformal field theories in a useful way. And of course, we in defining this sort of map of the space of quantum field theories, I've spoken about relevant and marginal operators. So as we're used to saying, we classify various operators O by their dimensions. So there are, of course, 3 cases. If we're in D space-time dimensions and the operator O has scaling dimension delta, the way we usually think about this is delta is less than D, equal to D, or greater than D. Good. So these are, of course, relevant, marginal, and irrelevant deformations. So as I've drawn, the relevant deformations trigger conventional renormalization group flows from an ultraviolet to an infrared conformal field theory. If there are exactly marginal directions, then they parameterize some conformal manifolds and coupling constants for those conformal, so those exactly marginal operators kind of parameterize the moduli space of the theory. And then the more confusing case is of irrelevant operators, high dimension operators, which we can think of as kind of going in some strange way back upwards to higher energies. But those are typically under poor control, because if one adds an irrelevant operator and then attempts to flow to higher and higher energies, you will generically turn on infinitely many additional operators and lose computational control. That's the usual story. So now I'd like to focus on the review part. So part of what makes this TT-bar deformation interesting is that it falls into this latter class of irrelevant deformations, in particular in 2-dimensional field theories, but nonetheless is under good tractable control in a sense which I'll make precise. Okay, so let me make that a little more quantitative. So now consider a 2D field theory. With a stress tensor operator, say T mu. Good. So the nice thing about these deformations that we construct from the stress tensor is that they'll be universal in a particular sense, because every translation invariant field theory has a stress tensor thought of as the Noether current for translations, or if you can couple to gravity, you can think of it as the Hilbert stress tensor for coupling to gravity. And if we were trying to construct a deformation of a two-dimensional field theory built from T, what you might think to do is to enumerate the Lorentz invariants that you could build from the stress tensor. The stress tensor is a second rank tensor, symmetric, of course. So any 2x2 matrix, which is what the stress tensor is in components, has only two independent traces that one can construct from it. So you can construct the trace of T, if you like, which is T mu mu, and the trace of T squared, which if you like is T mu nu, T nu mu. And these are the only scalars, Lorentz scalars, that can be constructed from this object. Any higher trace, trace T to the n, for instance, will be related to these objects by a Cayley-Hamilton theorem, or if you like, some trace identity. Okay, so in two dimensions, this is all you have. Of course, if we were in D greater than 2, then there would be other objects, trace T to the I, or I equals 1 up to D. So we'll keep that in the back of our minds for the moment. But for now, we'll restrict to 2 dimensions. Okay, so any putative deformation we would like to construct from the stress tensor should be a Lorentz scalar, which means it's in 2 dimensions built from these 2 objects. So a deformation will be some operator, say O of T mu nu, which in this case is some O of these 2 independent traces. So trace of T squared. Okay. So the first thing you might try to do is to say, well,
can I, okay, this statement that the deep portrays how higher powers of T is related to like the lower powers, like,
yeah.
But that's a systematic statement, right? It's even if you consider them as operators, it's a fine statement, is it?
Well, okay, that statement indeed. So this statement is a statement about 2x2 matrices, but the components of the matrices are indeed operators if we're thinking of the quantum mechanical theory. So it will still be true if you have a matrix of operators that, formally speaking, any trace, say T cubed, will be related to the trace of T and trace of T squares, because that's merely a statement about a matrix with entries in any sort of ring, essentially. So it's even if these are operators, you can expand out a combination like trace of T cubed, and it will be related by trace of T squared and trace of T. Right, so that's generic.
Is it because T is protected and things like that? Is that?
I think one doesn't even need to assume things about protectiveness of the operator. So this is purely an algebraic statement, right? If we're taking higher power, there's only 4 components of the stress tensor T. So if you formally expand out a combination, say trace T cubed, it'll be a product of a collection of operators, which will be the same as some products of the trace of T. It will be a symmetric polynomial, if you like, in trace T and trace T squared. So I think that will be generically true.
But typically, even dimensions change and change and so on, right? If you take products of operators, the dimensions don't simply add up and so on. But like this naively seems to say, like, if you say for any operator it's true, then you'd also expect the dimensions just multiply and add up and things like that.
Oh, I see. So you're worried about the dimensions of something like trace T.
Basically, the collection, because you're not thinking of them as operators.
Oh, I see. Good, good.
That's why I asked if it's because T is protected and so on. Exactly.
I understand. Okay, good. So good. I think I misunderstood the point of the question. So from that perspective, I agree. So then if we are caring about the dimensions of operators or protected properties of T, then we'll want to restrict to particular combinations of T, like TT bar, which I'll introduce in a moment, where there are nice properties of the combination. But for this statement, that higher traces like trace T cubed and T fourth and things like that will be related to the lower traces, then I guess if we're thinking about operator dimensions in the way that you'd like to do, then we should restrict purely to a classical statement. Okay, good question. Other questions about motivation? Okay. So there's a preferred quadratic combination. So the first thing you might like to do since the second invariant, the trace of t squared, is quadratic in t. So the first thing you might like to do is to form some homogeneous combinations. So we'd like something which is built from bilinears, products in t, which means it can only depend on trace of t squared and the square of the first invariant trace of t. So a generic combination would be a sum of some C1 times the trace of t squared and some C2 times the second combination, the trace of the square of t. But there's a preferred choice of those coefficients, which defines this TT bar operator, which can be written as 1/2 times the trace of the square minus the square of the trace. So this is a particular choice of the coefficients. So what makes this nice? Well, kind of alluding to the question that we had about protected operators, there's something which is special quantum mechanically even about this combination of operators. So this is nice for several reasons. So the first is that indeed, although we can make any combination of stress tensors that we like to form some classical combination that we'd like to deform a Lagrangian by, you might ask whether that combination actually defines a local operator in the spectrum of the theories, which will generically not be true. But for this particular combination, this actually does define a local operator by point split. So what do I mean by this? I mean that if we take a point split combination, insert it at 2 points in the field theory, where I take each of the stress tensors and evaluate them at a different point. So I take a combination like this, and then take the coincident point limit as y approaches x, which now involves products of local operators at coincident points, which is generically a divergent quantity in a quantum field theory. But it was shown by Zamolodchikov years ago that this particular combination in that coincident point limit does in fact define a local operator in the spectrum of the theory up to some ambiguities involving total derivatives, which can be neglected in the case where we're, for instance, adding this to an integrated Lagrangian on a spacetime without boundary. So this is the first surprise, that this quadratic combination is very nice, insofar as it defines a universal operator in the spectrum of any two-dimensional quantum field theory. And this is a quite generic statement. It only relies on translation invariance. It does not require conformal invariance. So this is not a statement about CFTs. It's about generic QFTs. And in fact, it doesn't even require rotation invariance or relativistic invariance. So there's a non-relativistic version of the TT bar deformation that does not require boosts, only translation invariance. So this is very powerful for this reason.
So it doesn't require symmetry of T.
Sorry, it doesn't require symmetry? No. So indeed, so in the case where the theory is not boost invariant or rotation invariant, T will not be symmetric. But indeed, you can still define this combination even in the case where T has an anti-symmetric part. That's right. Good. Other questions? Okay. So what else is nice about this combination? I've already argued that it's universal in a particular sense, that it's quantum mechanically well defined. Another nice property is that if we add this integrated local operator to some theory in order to deform it, observables in the deformed theory. What do I mean by observables? Lewis reviewed some of this yesterday, but this includes, for instance, the finite volume spectrum. If you put, say, the 2D theory on a cylinder of radius r, also the torus partition function, and the flat space F matrix, among some others, but these are kind of the first nice ones you might think of. These observables can be related to quantities in the undeformed theory. So this is the reason why people sometimes say the TT bar deformation is solvable. So from my perspective, the word solvable means that one can derive flow equations, which are often differential equations, or in the case of the S matrix, it's addressing by a CDB factor, which we saw yesterday. These are explicit expressions that tell you how to compute quantities in a deformed theory in terms of the corresponding quantities in the undeformed theory, which is another very nice property. So in the picture of a space of quantum field theories that we had at the beginning, we can think of this as kind of starting from some isolated point, which maybe we understand very well, some seed theory or undeformed theory, and then kind of pushing out a trajectory away from that theory to find a line or a one parameter family of deformed theories, which are also under control, in which we can still do computations. So that's very nice because it extends, for any well understood theory, it extends our understanding to a line of theories for which we can also compute quantities. Now, a third interesting piece of data about this deformation is that if one deforms a conformal field theory, so a TT bar deformed conformal field theory, has a high energy density of states, which no longer exhibits Carty growth, which would be required of any local quantum field theory, but now has Hagedorn behavior. So what do I mean by Hagedorn? Specifically, I mean that if we write the density of states, say rho E, or sorry, rho of En, at large En, this goes like an exponential, not of the square root of the energy E, but up to some prefactor, where here lambda is going to be the TT bar parameter by which we deform. The density of states is proportional linearly to the energy of the theory, not to its square root. So this is a faster growth in the high energy density of states than would be expected for a local quantum field theory. And in fact, is more reminiscent of a string theory. So string theories have a Hagedorn growth of the density of states at high energies. So a TT bar deformed conformal field theory is a somewhat strange object. We began with something like a field theory or a CFT, and we've deformed by adding some integrated local operator of this form, and somehow ended up with something that looks something more like a string theory, which is kind of bizarre. Bizarre and interesting. It's a hint that there's something nice about this. Good. Questions about the nice properties or any of the motivations? Yeah.
So these properties valid in any curved spacetime, such as polar or genus polar.
Any space-time manifold you're saying?
I think property one is for the infinite plane.
So this, yeah, so usually, so in order to, well, let's see, this thing is a local property. So by point splitting, this is true on any space-time manifold. That's correct. Here, there's particular choices that are being made. So for instance, for the finite volume spectrum, we're specifically thinking of a cylinder. The torus partition function, of course, we're taking a trace, so it's kind of implicitly forming a torus. The S matrix is specific to flat space. But you can ask more generally about what happens if you try to deform this on, say, a two-dimensional space-time manifold, say, with a metric, for instance. So then things become somewhat more complicated. So for instance, if you want to define TT bar on an ADS type space-time, kind of constant negative curvature like the Poincare plane, you can do that. That uses the special properties of ADS. If you try to do it, say, on a sphere, you'll run into issues with some steps of the derivation because, for instance, in order to prove this so-called factorization property of TT bar, which I haven't written down yet, you want to use a type of cluster decomposition where you take insertion points far away, and you won't be able to do that on a sphere. So in the sphere case, parts of this will apply, such as the definition by point splitting, but other parts like the factorization will not apply.
So usually for the operator product, don't we define by point splitting, at least one way of defining the product is by point splitting. Why is it special in this TT bar?
Good. Yeah. So indeed, we could think of this property as, say, taking the OPE of this particular combination of stress tensors and then looking at the coincident point limit. And what's special about this combination is that, indeed, even though there will be divergent terms in the OPE as you take the points close, what you'll find is that for this combination, every sort of divergent term in the OPE will be proportional to a total derivative of some other local operator with a diverging but constant prefactor, not an operator prefactor. So what's nice about this is that if we want to use this to write down, say, some flow equation, which is of the schematic form, say, d Lagrangian d lambda equals PT bar at lambda or something like this. So if we're inserting this into an integrated quantity, like the action, which is the integral of the Lagrangian, kind of morally speaking, all of those total derivative ambiguities drop out. So up to total derivatives, we can think of this as being sort of a regular sort of OPE, right? The divergent pieces are all total derivatives. Good. Other question? Yes.
So in property 3, do you assume that you start with some rational CFT, or do the details matter?
As far as I know, the details do not matter. So this is a statement about deforming any CFT, which has, I think this really only depends on the statement that in a CFT, the undeformed energies are going to all be essentially, they're constants divided by, say, the radius of the cylinder that you're looking at, which is a statement that's true of any conformal field theory, regardless of the operator dimensions or central charge or anything like that. Good. Any other thoughts? Okay. So these are some of the reasons why TT bar in particular is interesting. Now, even though these properties largely concern the quantum mechanical definition of the theory, I want to now point out one way of seeing some hint that this might be connected to string theory. So this third point here, that there's a high energy density of states, which is Hagedorn, that seems somewhat stringy. There's a way to sort of motivate this, or a hint that this might be true, which is purely classical, which is to say that if we study this flow equation, so if we study the flow equation, again, d Lagrangian d flow parameter lambda equals the TT bar operator defined at the theory with that particular value of lambda. So this is, again, thinking of, say, some flow or some one parameter family of theories where we start with an undeformed theory L0 and then proceed along a curve where at each point on the curve we deform by this combination TT bar evaluated using the stress tensor T of the theory at that point along the curve. So this is defining a continuous flow in the space of field theories. And now you could say, well, I'd like to view this purely as a classical problem in differential equations. So I'm going to view the Lagrangian as simply a function of kind of my classical field variables. For any such function, I can compute the stress tensor, say, using the Hilbert definition. And then I can get some differential equation, which gives me, say, some ODE or PDE for the deformed Lagrangian L. And if I begin with an initial condition for that differential equation, which is just a free scalar, say d mu phi, d mu phi. This is a quick exercise. You can solve this. It turns into an ODE in one variable, which is the product of lambda with this combination d phi, d phi. And the solution is very nice. So there's a solution L lambda, which looks like this. Root 1 plus 4 lambda d phi minus 1, if I got the factors right. This is originally due to Roberto, so I realized that speaking about this in front of him is a bit like bringing sand to the beach. But this is a very nice result because this Lagrangian is the description of the Namagoto string, gauge fixed to static gauge, in 3 dimensions. So there's kind of one transverse direction phi, and then the world sheet has a tau and a sigma type direction. So this is a hint that the TT bar deformation of a CFT, in particular a free scalar, is indeed related to string theory, as we saw from this density of state statement. Okay. So now I'd like to motivate a little bit some of the more speculative ideas that I'll talk about later. So if we think about how one might want to generalize TT bar to higher dimensions, all of these properties that I discussed here are special to the two-dimensional case. So the definition by point splitting, all of these nice statements about observables, the quantum properties are unique to two dimensions. But let's allow ourselves to be a little bit more speculative and ask, what guiding principle might I use if I want to look for some nice analog of TT bar in higher dimensions? And if we say, well, this was a very nice property that the deformation of a free scalar gives me an action that looks like string theory, you could ask yourself, can I construct some analogous operator for a higher dimensional theory, which also gives me a stringy type action? I mean, maybe that's a nice thing to do as a first step. Okay, well, let's investigate that question. So if we now lift to D dimensions, so in D dimensions.
Elementary question.
Yeah.
Starting from this Lagrangian, can I derive the number 3?
Sorry, starting from this Lagrangian, can you derive?
L lambda, the TT bar deformed Lagrangian.
Oh, this one, yes.
Yeah, then can I derive number 3?
Oh, good. Okay, so there's a subtlety. So this is indeed the Lagrangian for the Nabu-Goto string. So if you begin with this as your starting point and said, I'm going to study string theory in the conventional sense, then you would conclude, yes, it is the case that string theory has a high energy density of states, which is Hagedorn. So in that sense, they're related. But the subtlety is that it's not literally true that TT bar deforming a theory with a given classical Lagrangian for the undeformed theory, and then finding some deformed theory, and then quantizing the deformed theory would be the same as deforming the original theory with the quantum definition of TT bar, for instance, by looking at observables of this form, and then comparing that to the final result. So I said that in a confusing way. Let me say it differently. There has been work, for instance, on looking at loop corrections to TT bar deformed theories. So you might say, I'd like to look at a TT bar deformed scalar or fermion or something like that, and say, well, on the one hand, there's a deformed classical Lagrangian of this form, but on the other hand, I have a different definition of the quantum theory, the TT bar deformed theory, using one of these properties, like the torus partition function or the.
I understand. My question is, can you quantize that directly, or will you reformulate that? So, yeah.
Right. So
can you derive that honestly from this section to number 3?
Good. Yeah. So I mean, one can quantize this directly in the usual way that one does in string theory. So for instance, what one would want to do is introduce a background metric and go to the polyacop formalism and quantize in that way. The answer I'd like to give is that if you do that procedure of coupling to a background metric and then quantizing all the string theory, you will find this statement. So in that sense, it's true, but in another sense, it's somewhat misleading, because in general, quantizing the classical Lagrangian obtained by solving a TT bar flow will not necessarily agree with the properties of the TT bar deformed theory if you use one of these quantum mechanical definitions. These things, in general, they will not be the same. That's the subtlety. Good. Other questions?
So -1 behind the square root is for lambda to 0 limit is well defined. What is the interpretation in terms of the old CTI of the constant -1?
Sorry, what's the definition or the interpretation in terms of what was it?
In terms of the string theory, so what is the interpretation of -1 behind the square root?
Oh, the -1. Good.
So someone says about the B field or RMB.
That's right. Yeah. So you can think of the -1. There's some work by, I think, Alessandro on this who will be speaking on Thursday. So from the string theory perspective, you can think of the -1 as coupling, say, constant B field. So this is like some B mu integrated over the world sheet to give some constant. So from one perspective, there's a particular choice of flat B field to give this constant. But from a different perspective, you could say, well, I'd really just like this -1 so that indeed the lambda goes to 0 limit of this reproduces the free scalar, because at small lambda, you would need to expand the square root. So this would be like 1 + 2 lambda d5 d5 or something like that. But I'm dividing by lambda. So from a different perspective, you could think of the -1 as simply fixed by the initial condition of this differential equation so that it reduces to d5 d5.
Thank you. Only is there a reason to fix the specific details or?
Oh, to pick the specific ones? Good. So I don't know. I don't have a good a priori justification for why to pick this particular choice of B field. There is some work relating TT bar to TSC, which we heard some of yesterday. And from the TSC perspective, you would generate a constant B field by doing one of these TSC type transformations. So this is discussed a little bit in some of Alessandra's papers that relate TT bar to this uniform light cone gauge, for instance, that would motivate this B field. But from my perspective, the full physical understanding of that sort of perspective isn't totally clear. So you can use that if you like it, or ignore it if you don't, I guess.
As for the lambda parameter, is it related to RG or?
In a sense, so people sometimes say that the TT bar parameter lambda is kind of like going up their normalization group. So it's kind of like a parameter along a curve that starts at a field theory and then goes up into the UV. But in a sense, that's somewhat misleading because an RG trajectory, almost by definition, is a one parameter family of local field theories as the scale is varied. And the lambda parameter, as we've seen here, it's connecting CFT in what would be the IR to a collection of theories that are no longer local quantum field theories. They have a Hagedorn density of states. So it's like an RG flow, but it's not a conventional RG flow because the points along the flow are no longer local field theories.
Well, let me rephrase in the language that I learned in class, quantum field class. In the RG, so we can just integrate out from the higher energy mode after some cutoff scale or whatever, right? Then we are getting toward the lower and lower effective theory, which will produce many other Riemann terms, right?
Yes.
So in the case of irrelevant operator, they are becoming much suppressed, right?
Mm-hmm.
So there will be some questions that depend on the scale. So maybe some lambda is related to those parameters that we expect to obtain in front of the irrelevant operator.
That's right. So from that perspective, indeed, since maybe one way to see it is by expanding out the square root. So this would look like, in an expansion, it would look like the undeformed theory d phi, then plus a lambda d phi to the fourth, and then some other lambda, some number times lambda d phi to the sixth, and so on. So indeed, from an RG perspective, you would say, as I flow to longer length scales, I would integrate out these higher dimension operators, and they become more and more suppressed. Sorry, lambda squared. So indeed, from that sense, it's kind of like an infinite collection of operators that are suppressed at long distances. Good. All right, very good. Other questions? Okay. Very good. Halfway through. All right, so onwards to looking for analogs of this in higher dimensions. So in D dimensions, you can quickly convince yourself that if you try to run an analog of this story, so you might say, well, I would like to look for an operator which gives me the Nabubotu action or some string theory type action beginning with a free scalar in D dimensions. And you might think, well, the first thing that I'll do to attempt to find such an operator is make an ansatz. So in D dimensions, I'll say my differential equation will be D Lagrangian D lambda is, say, some number C1 times the first trace invariant, the trace of the stress tensor squared, and then some other constant C2 times T mu. And you would try to choose these constants so that the same property holds, that if you begin with a free scalar theory, you will find something with a square root. So that's the first thing you might try to do. And you will find that that fails. So there is no choice of C1 and C2, which makes this work. In more than 2 dimensions. Okay, so that seems somewhat discouraging, but then you realize that, well, when there are more than 2 space-time dimensions, the stress tensor is now a D by D matrix for larger D, so there are more invariants that I can construct from the stress tensor than just T mu nu and T mu nu, the trace of T and the trace of T squared. So there are other things that we could include. So there are other invariants that must enter. So a priori, you might think that this will become a very complicated problem because by this Cayley-Hamilton type argument, in d dimensions, there will be d traces, trace of t, trace t squared up to trace of t to the dth power. And there will be many, many coefficients, C1 up to CD. Maybe you have to take different powers of these and tune the coefficients in some way in order to get a square root type solution. So it could have been a very complicated problem. But as it turns out, there's a simpler resolution. There's a way to get a higher dimensional generalization of this that only requires introducing one more invariant. So let's introduce a particular combination, which I'll call O sub root TT bar. What is this? Well, I'll tell you the normalization later, but this will be a particular combination that looks like T mu nu minus 1 over the space-time dimension times the trace squared. And if you like, you can think of this as being built from the traceless part of the stress tensor, because if I define this traceless part, lowercase t mu nu, as capital T mu nu minus 1 over d times g mu nu times the trace, then the combination under the square root is just lowercase t mu nu, uppercase, or lowercase t mu nu, lowercase t mu nu contracted. So this is the contraction of the traceless part of the stress tensor in d space-time dimensions with a square root. Now this is a very strange looking combination, but remember for the moment, all we're trying to do is play games with classical Lagrangians and differential equations. So we don't need to make sense of this as an operator at the moment. We're just treating this as some combination that can appear inside our differential equations. Okay. So now there's an exercise one could do. So this is a high school level calculus exercise, which is somewhat relaxing if you'd like to, I don't know, fix coefficients someday when you're very bored. But the game is as follows. So now
I could also make this operator by just adding the operator without the square root, but then summing all the coefficients with some weight.
Yeah, so indeed, yeah, you can always, good. So almost by definition, there's a ring of scalars that can be constructed from a d by d matrix, which is traces of powers. And because it's the ring, a basis for the ring of scalars, any other scalar constructed from T can always be expressed in terms of those things with various coefficients. So that's true. This can always be written as some function of all of the trace of Ti for I equals 1 up to D. However, the expression for this particular combination in terms of all of those traces will be dimension dependent. So I prefer to present it in this way because this is the same operator up to this factor of D in any number of dimensions.
What I meant is like I could add the square of O square root T bar with some coefficient, and then do a weighted sum with some, add some weight, do some Steckelberg kind of thing to stimulate this O root T bar.
Wait, sorry, I don't know. So you want to generate?
I could add a lambda or square, or root T bar square, and then add under square root lambda or something and integrate over lambda. What I'm saying is like if I added the square root of O with some specific lambda, and provided I know it for all lambdas, provided I know such theory, those deformations for all lambdas, I would essentially get the information about this deformation.
Okay, so you're saying you want to generate this operator by using the
square of this operator, but then like do a Steckelberg on the parameter of the deformation.
Yeah, I see. So it's kind of analogous to doing like almost like a Hubbard-Shatanovich sort of thing or something to generate.
Yeah, Hubbard-Shatanovich, not Steckelberg. Sorry.
Yeah. No, I agree. That you could do. Good. Yes, that's for sure. That's actually
Trying to understand is that like very different from what was nice about this operator again that it gave a deformation like this.
Yeah, well, at the moment, as I haven't told you anything nice about this yet, it looks very strange. So I'll say in a moment that one thing that's nice about this is it allows us, if we add an additional term to this, it will allow us to generate this stringy type action in any number of space-time dimensions, again, as a classical flow equation. So indeed, if you want to do something like, for instance, look at a path integral type argument or an argument like John Cardy's argument for the regular TT bar in terms of random geometry, but using this operator, then it might be nice to use some Hubbard-Shatanovich type argument that might give you some additional power from presenting this operator in a different way. But for the moment, I'd just like to solve the very naive question of how to get string theory from a deformation of a free scalar. So in that case, it doesn't give me anything to use a Hubbard-Shatanovich, for instance.
But is there a way to get exact number go to action of say 26 scalars interacting or something? Is that
By exact, you mean do I get sort of the d-dimensional version of this, for instance?
of like so many of the scalars interacting like in worldsheet action like.
Oh, well, sorry. Well,
Without the in one inside the square root and so on. Like.
Maybe you are doing like not the string worldsheet action, but the world volume.
No, I just mean worldsheet action, but I need x mu instead of del phi. Del x.
You want multiple scalars? Or,
Yeah, that's the multiple scalar version of this, right? The worldsheet action is.
Yeah, I agree. So indeed, this action is only this. We've written three-dimensional target space string action, but indeed, if you want, say, a d-dimensional target space action, then you would have to put a collection of indices I on this, and in this case, there would be a second term that comes from expanding. It's essentially the root det of the Namugoto action, which you would have to expand out. But I'm doing only a single scalar, which is like a string in 3 target space dimensions for simplicity.
So could you say why is the string in 3 target space dimensions? The mu's are 1 and 2, right? I thought the mu's are like worldsheet dimension.
The mu's are 1 and 2. The i's run from 1 up to d, where the target space dimension, since we're in static gauge, is d plus 2, right?
Right.
Yeah, so indeed, so if you wanted to generate, say, a 10-dimensional or 26-dimensional string action, you would put I indices on this and let the i's run over however many you need. But I've suppressed the i's and just done a 3-dimensional.
But is there a way to get the exact number go to action without this extra 1 factor inside the square root and so on?
This 1 factor is there for the Namugoto action, right? If you expand root det, eta plus d phi d phi, you'll get, say, this in this case, right? So the 1 needs to be there.
Okay, it's like in light corners.
In static gauge, yeah. Yeah, this is the same as kind of root det, I guess, eta plus d phi for the 3-dimensional string. And when you expand the root det, you'll get the 1, right?
I could replace the string action as a TT bar float ordinary QFT.
That's right. Yeah, that's the claim. But you could define, if you didn't know the Namugoto action for a worldsheet theory, a 2-dimensional worldsheet theory, you could say, I will define that action as the unique solution to the TT bar flow in 2 dimensions, with the seed theory being a free scalar. And then
Just one more question. Do people try to like extract meaningful asymmetries out of these actions?
out of this,
In a string theory sense, like with multiple geometries of various topologies and so on, do people also try to extract?
Oh, to do like a string worldsheet path integral or that sort of thing from this perspective.
Kind of thing from this.
No, so in fact, it's slightly different. So, I mean, this, even though this gives you the classical Namugoto action by deforming, say, the free scalar, the subtlety I was alluding to before is that a TT bar deformed conformal field theory looks like a string theory in some sense, in that you get this, but it's not literally the same as a string theory in some other senses. So, for instance, the usual way that we think about string theory in the Polyakov formalism has dynamical worldsheet gravity. So there's a worldsheet metric gamma, for instance. But the TT bar deformed theory does not have dynamical gravity. So you can think of it as some coupling to topological gravity or this random geometry or something like that. But it's not quite the same as string theory in the Polyakov formalism. So as far as I know, no one has attempted to use this approach to compute string theory observables like a string scattering or a worldsheet path integral or something like that using a deformation, because the theories are slightly different. Good. Other questions?
So there is no deformation we can define so that you directly land on Polyakov formats, and that's what you meant?
Yes, that's what I mean. So I don't know how to do a deformation of a 2-dimensional CFT and obtain the full Polyakov string theory action. That's right. I only know how to do this deformation, which gives me some somewhat more mysterious theory. I think it's fair to say that it's not fully understood what type of theory a TT bar deformed CFT really is. It appears to be somewhat like a field theory and somewhat like a string theory, but not quite either of them. So it's not what you would want to do for ordinary string theory computations in, say, the Polyakov formalism. Good. Yeah.
Maybe I missed your saying at some point, but is that all scalar TP bar flow equation are satisfied by the Lagrangian with the d-dimensional generalization of that Lagrangian?
In the two-dimensional case, you're saying is this?
That is the 2D case, and we can generalize the mu to 0 to d minus 1. So we can generalize it into the d-dimensional case. And I want to ask whether the d-dimensional generalized Lagrangian satisfy the old scalar TP.
Oh, right. So you're asking what flow equation do I need to write down in d dimensions in order to get this sort of thing? Like, does this appear in it? That's good. Good. Okay. So I was about to write that down and answer that question, but I did not yet. So maybe I should do that. And then if it doesn't answer your question, then you should ask me again. But the statement I was going to make is that in d dimensions, if we make an ansatz of the following form, so d Lagrangian d lambda, we'll add in one more term. So the trace squared piece is still there. There's the quadratic piece, which looks like this. But now say you add an additional term, which is a product of this O root TT bar and the trace. So this is still an irrelevant flow. All of the terms have the same dimension as the square of the stress tensor, right? We have t squared, and here it's t times something with dimensions of t, because the O root TT bar is like a root of t squared, which has the same dimensions of t. So my claim is that if you make an ansatz of this form and ask what coefficients do I need in order to generate the Namagoto action from the free scalar in d dimensions, you can solve this problem. And you'll find that this works if you choose the coefficients in a particular way. So the C1 in terms of, in front of the trace squared piece, the C1 needs to be, say, 2 over d squared. The C2 will be minus 1 over d. And the C3 will be 2 times the quantity 2 minus d over d squared. So now we see why in 2 dimensions, you did not need this term at all. So in 2 dimensions, 2 times 2 minus d vanishes, so this term goes away, and we didn't need that at all. But in higher dimensions, if you want to generate this Namagoto action from a free scalar, you need an additional term with some coefficient chosen in the right way. And then the claim is that the flow equation here with these coefficients, and again, this initial condition, will give you string theory in d spacetime dimensions. Was that the question? Okay.
And inside of square root, is it positive definite or?
Yes, I think the way to see it, good. So to see the positive definiteness, it's perhaps easier to write it in terms of the traceless part, because in terms of that, this will look like the object under the root t mu, just t mu, t mu nu. So that's this combination under the root. And the t mu, t mu nu will indeed be positive definite. It's kind of morally a complete square, for instance.
Even in the Lagrangian, or here you are to just Euclidean, it doesn't matter.
Oh, good. So I'm implicitly thinking of Euclidean in my head, in which case this will genuinely be positive definite because all of the signs are positive. I think, I forget the argument, but for some reason, I think I convinced myself at some point that it's still positive definite for Lorentz signature. I'd have to check why that's true. But certainly for Euclidean, at least it will be true. Good.
So is it a new result? Is it already published?
No, so this is work in progress that will appear shortly. So this is somewhat new. So I'm previewing some new work. But
and really you get the Namagoto like the static gauge, this lambda, L of lambda in higher dimension. Is it?
That's the claim. So the claim is that that flow equation in d dimensions has this solution. So it generalizes your 2-dimensional results to d dimensions. That's right. Good. Yeah, this will appear shortly in work with Gabriela Tartaglino Mazzucchelli and Konstantinos Koutrilakos and Young-Marie Hu. We're working on both this, the statement about the scalars, and then also an analogous statement for gauge theories, which I think I have enough time to tell you about.
Can you put together also Maxwell this Bohr-Infeld with scalars. Can you put them together?
Good. That's an interesting question. So you could, what we found so far is that you can do this for scalars. And on the other hand, you could tune the coefficients so that if you begin with Maxwell, it gives you Bohr-Infeld. But it seems that in the cases we've looked at, that the coefficients are different. So you would like to find a case where the coefficients that would give you the scalar square root and also the coefficients which would give you Bohr-Infeld would be the same. So you could combine them and get the DBI. And that we haven't managed to find yet. There may be a way to do it, but at the moment we haven't gotten that to work. Very good.
Can you say again this like in higher dimension you have a generalization of this number? What type of the generalization of the number? It's just world volume.
Yeah, it's not really a generalization at all. Sorry, I've written too many things over this formula, so let me just rewrite it. The claim is just that if you want for a single scalar,
In the square root.
yeah, you just want to get the square root. So there's no generalization in the form of the actual solution. The only generalization is that this will be the solution to the flow equation for a d-dimensional scalar with this seed theory.
Just the inject.
That's right. Yeah. So that's right. This is just it's just a very naive question, just asking how can we get this as the solution to a flow and d greater than 2. Good. Other questions?
So that still looks like a world sheet action, right? It's not like a world volume like pizza.
Oh, you're saying this? Well, yeah, indeed. So this will be well. Sorry, when you go to d dimensions, it is a world volume insofar as the d dimensions refers to the number of coordinates that the scalar field depends on, right? So this is x1 up to xd, right? Since this isn't the number of target space dimensions, if you like, the number of target space dimensions would be related to the number of scalars phi I. Here, when we say d-dimensional, we mean that kind of phi is a function of d coordinates, which would be like a world volume when d is greater than 2, right?
Then it is saying like this first term usually coming from static gauge in the RC case. This case, for this case, also.
Oh, the first term being the 1, for instance.
Yes. So.
Yeah, I think
there are some. Yeah.
Yeah, there'll be some other combination. I guess. Let's see. If in general, this should really be kind of root det of kind of metric plus d phi. Right. So yeah, so you'll expand out, and there will always be some constant term appearing here from the eta when you expand it, and then there'll be a combination of derivatives. That's right. Good.
This is also work for spinors.
Oh, for fermions. Good. So it's tricky. So we thought a little bit. I might mention this in the other talk. We thought a little bit about including fermions in the 2-dimensional case. So for instance, to do supersymmetry, something like that. The tricky thing is for a theory of just fermions, you're going to get into trouble writing down a combination of this like this form, because the object under the square root in that case will be purely Grossman. And I don't know what it means to write down an operator that's a square root of a Grossman quantity, like the square root of, I don't know, psi d psi or something like that. That doesn't make sense by itself. But if you have a theory with both bosons and fermions, then the combination under the square root will have some kind of purely bosonic component that's just built out of the phi's, and then plus some fermions. And then you can Taylor expand the square root. So there'll be a bosonic part plus collections of fermions and things like that. So there are cases that we understand where you can include spinor fields or fermions. In components, at least. A more ambitious goal that we're working on is, can you include the fermions by using a superspace formulation in order to construct this object? And that seems to work in some examples. So we have a 3-dimensional example where it seems to be working, where you can supersymmetrize a theory and then write a combination of this form as a superspace flow. So you lift to superspace, and then replacing the stress tensor will be the supercurrent multiplet that contains the stress tensor and other fields needed for supersymmetry. And then you can write a manifest superspace flow, which has this solution as its bosonic truncation, but then also has a fermionic completion. And that seems to be the more elegant way to include fermions, I would say.
But in the case of TT bar, it's better, like this is general dimensional statement you're making, right? Just in the case of two dimension and TT bar, is it clear how does this generalize for if you have a fermion?
Oh yeah, so that was worked out years ago by me and also some collaborators that you can supersymmetrize the regular TT bar as well. So the statement I made about a superspace flow, that you can do in any two-dimensional field theory with 0, 1, 1, 1, 2, 2, 0, 2 supersymmetry. Those are all worked out, and you can find the analog of TT bar in superspace, which includes the fermions very naturally. That's one way to do it with superspace. You could also do it in components if you like. You could TT bar deform without using our formulation in terms of superspace. You could do the regular two-dimensional TT bar, just writing down the component action. There things become somewhat more complicated because when you deform, the supersymmetry transformations will also be corrected order by order in lambda in a fairly horrendous way. So this is part of why we wanted the superspace formulation, because once you present things as a superspace flow, the action of the supercharges is kind of canonical. It just acts in the same way. Good. Other thoughts?
So I have a question, but maybe do you have many so almost 1 hour, but you can keep going, but so
yeah,
just let me know how long do you.
No, I mean, I have a flexible endpoint, because I was hoping there would be a lot of questions.
Okay.
So
Yeah, then maybe can I ask? So here you mentioned the relation to this scalar action. But, do you have also nice property on this some spectrum or any other? I don't know. Here, estimate in higher D, you cannot have estimate. Maybe estimate is possible, but this CDD, this CD factor or this kind of thing is only in the 2D. But do you have all the nice property in the 2D TT body formation in this higher dimensional scalar T, or?
Yeah, it's a very good question, and we don't. So even, as I'll discuss in the next talk, even in the two-dimensional case for the two-dimensional root TT bar, I don't know how to obtain the deformed spectrum or the deformed S matrix. So it's not clear to me that those properties of the two-dimensional TT bar carry through to root TT bar if you include those types of flows. I will explain that there are some properties of the two-dimensional TT bar that also hold for deformations involving this quantity. So for instance, it's known that the two-dimensional TT bar preserves integrability, and as Alessandro will tell us on Thursday, a root TT bar also preserves integrability in a collection of models, the principal chiral model, nonlinear sigma models with target spaces that are either cosets or semisymmetric spaces or something like that. So there are many hints that these deformations are also nice and that they preserve a lot of the structure. But unfortunately, the answer to your question is I just don't know about the S matrix or these other things. I'd be very interested to find out the answer to that, though.
Then what about the factorization? Then maybe the first, you in the TT bar deformation, you mentioned that this is local. When you can do this point split, a nice homological for the people did. But here also, can you do the similar regularization?
Right, that's another good question. So that would be, I think, the first step to understanding something like the spectrum or these quantum properties would be asking, does this operator in 2 dimensions even exist in the spectrum of a theory?
Yeah.
And I'll tell you why I think that's a subtle question, because in 2 dimensions, if we had a proof in Holozomologikov that you could point split and define root TT bar in a universal way, then that would mean that given any 2-dimensional field theory, I can construct a marginal operator and therefore a marginal deformation. Now, I think that cannot be true, because there are 2-dimensional field theories like the Ising model that have no marginal deformations besides disorder, for instance. So I think there cannot be a proof on Holozomologikov that the 2-dimensional root TT bar has a universal deformation by point splitting. But I think it might be true that in particular examples with additional assumptions, like say a collection of bosons or something like that, in those models, it might be possible to deform it and show that this is in the spectrum of the theory. And that's something that we're still thinking about. Good. Other questions?
Yeah, maybe I have more questions, but maybe it's too early to ask. But do you have any speculation of this deformation in the holography?
Yes, I will tell you about that in 1 hour. So
okay.
Yes. I'll preview if anyone is not sure whether they want to come to the next talk. I will preview. So as Lewis told us yesterday, the regular TT bar deformation in ADS3 CFT2 corresponds to particular mixed boundary conditions. So in the undeformed case, there's Dirichlet boundary conditions for the metric, and in the deformed case, there's a particular combination of the metric and stress tensor, which is held fixed. So we do have results. I will show you in 1 hour the explicit formula. So I can show you that the root TT bar deformation in 2 dimensions also corresponds to a particular choice of mixed boundary conditions on the metric, which looks kind of funny. It involves some Gaussian cinch sprinkled around in various places, but that I think is the holographic interpretation for root TT bar. As far as we can tell, it does not have a finite cutoff interpretation, though, the way that the bad sign regular TT bar does for lambda negative. In this definition, it seems to only have a mixed boundary condition interpretation.
But you would expect that from some Hubbard-Stuttles kind of picture, no?
For the mixed boundary conditions, you say?
Yeah, because you can do an average over the deformation parameter and then do a Hubbard-Stuttles to cook up root TT bar.
Yeah, I think you could certainly see it from that perspective, but I would take even a more naive perspective that just from doing holography, from doing ADS3 CFT2 holography at large N, I would have said that any operator that I could cook up that's built from the stress tensor, any f of t or something like that, I could do kind of the old path integral arguments that go back to the early 2000s and say that any such combination should correspond to a particular choice of mixed boundary conditions corresponding to some collection of derivatives of the operator that I'm adding. So that thing is not particularly special, I think. What is special, I think, about the root TT bar boundary conditions is that it has some additional properties, like it plays nicely with the regular TT bar. I'll show you later today that it commutes with the TT bar deformation in a particular nice way. So those are additional properties that wouldn't be true for just any generic combination that you would add. Good, okay. Well, I've unfortunately exhausted the time, but I'm happy to answer more questions over the next hour if people want to discuss.
Then maybe officially over and
yeah, that works.
Okay. Okay. If there is no more question, let's thank.
Welcome everyone to this afternoon session. We already had a talk this morning by Christian, which I must admit was a fantastic lesson in pedagogy. What an excellent talk. And we're looking forward now to Christian's second talk, where he will tell us about root TT bar deformations. So Christian, please go ahead.
Great, thank you very much for the introduction, and I'll thank the organizers again for the invitation to speak. So my previous talk, the informal talk, motivated a little bit why we might be interested in these sorts of bizarre deformations that involve square roots of stress tensors. And in this talk, I'd like to go into more detail and explain some results and also some work in progress telling us more about this type of deformation, in particular in two-dimensional field theories. Okay, so let's see. Yeah. Oh, there we go. Okay. Thank you. Good. Okay. So first, the motivation. This is, in some sense, a review of the review from the previous talk. But what is the big picture? So the broad motivation is that often in physics, we learn much about a system by beginning with a tractable case that we understand and then deforming in a controlled way, whereby I'll make the meaning of the word controlled precise in a moment. But an example of this is that given a quantum field theory, we can deform the field theory by adding an integrated local operator of the form like this, where O is some operator in the spectrum. And we had some pictures of different flows generated by different operators in the previous talk. But you might ask what criteria you would use to choose a desirable or a good operator for such a deformation. And I would make a wish list of kind of 3 nice properties that one would like to have. So in the best case scenario, it's ideal if your deforming operator O is something which is universal in the sense that it's present in the spectrum of either any field theory or a broad class of field theories that you're interested in. It would also be nice if the deformation is solvable in the sense that you can compute quantities in the deformed theory. And it's also nice if the deformation respects symmetries of the seed theory so that you know that they're still present in some way in the deformed theory. Oh, wrong way. Great. So as we saw in the previous talk, one way to achieve the first property, universality, is to build your deforming operator from the stress energy tensor T alpha beta of a theory. Since every translation in invariant field theory admits a stress tensor T alpha beta, if you can construct any well-defined operator from this T alpha beta, then you're guaranteed that that operator exists in the spectrum of any theory. And again, as we saw in the previous talk, a nice example of this is the TT bar operator for two-dimensional field theories, which I've written again here. So this is well-defined in the sense that you can define it quantum mechanically by point splitting, and it exists up to some ambiguities which we can ignore. And that's very good. So such universal deformations are extremely useful because, again, our motivation is to sort of explore the space of quantum field theories in some sense. And the existence of a universal deformation of this form is great because we can apply it to a large class of seed theories that are well understood in order to understand an even larger collection of deformed theories. So this is great for understanding quantum field theories. So since this is any stress tensor deformation is universal, and the TT bar type deformation has this solvability and the symmetries property, I'll quickly review the other nice properties that we mentioned in the informal talk. So the first one I've already alluded to is the point splitting definition. So you can define the operator quantum mechanically by taking coincident points, and this gives you an operator in the spectrum, a well-defined local operator. The second property, which I called solvability before, we also reviewed in the previous talk. So the specific quantities that one can compute in the TT bar deformed theory we've already mentioned are things like the spectrum partition function and so forth. And I also mentioned this high energy density of state statement, which looks like a string theory. And we also reviewed in the previous talk this statement that the deformed Lagrangian for a seed theory that is a free scalar looks like the novel go-to action of string theory, which is another nice hint that something is interesting about this particular deformation. So I've argued to you that this deformation is interesting. And in the previous talk, we also constructed other irrelevant deformations in higher dimensional field theories with interesting properties that looked like TT bar. But in this talk, I'd like to do something different. Rather than look for other irrelevant deformations like TT bar that might be interesting, I'm going to ask, are there other interesting deformations which in particular will be marginal deformations built from the stress tensor, which nonetheless possess some of the nice properties of the TT bar operator, which is irrelevant. So that will be the goal of this talk, other interesting operators. And in one slide, the proposal that I'll show you is that there's a classically marginal deformation that we can write down, at least for two-dimensional field theories, which we've already been introduced to. But now we're going to deform not by combinations of this operator and other stress tensor operators, which gave irrelevant deformations, but we now ask the different question, what happens in a two-dimensional field theory if you deform purely by this marginal deformation and nothing else? So this might look somewhat crazy. It's an object which is non-analytic in the stress tensor. So near stress tensor 0, near t equals 0, like a vacuum sort of configuration, this does not have any sort of controlled expansion around 0 because it's not analytic. So you may initially respond by saying this is crazy. So why would one have any right to expect that such a combination makes any sense? And that's a reasonable objection. So I will try to convince you with some pieces of anecdotal evidence in the remainder of the talk that even though this looks somewhat crazy, it might not be as crazy as it initially seems. So this was the introduction. This concludes the first part of the talk, just introducing the question. And in the remaining parts of the talk, I'll tell you sort of how one might go through and motivate and construct this root TT bar deformation, and then show you some solutions, some deformed Lagrangians for this deformation. Then I'll spend some time talking about holographic interpretation in the context of ADS3C and T2. And in the end, I'll summarize and explain some of the many open questions and future directions related to this operator.
Can I ask a question?
Yes, please do.
In the TT bar case, like, is there a holographic interpretation of the Hagedorn spectrum?
Oh, good. Let's see. So there's certainly a holographic interpretation in terms of mixed boundary conditions. So you say, how do you see the Hagedorn? Let's see. I don't know of a way to see the Hagedorn behavior holographically. And if I were going to, I don't know if this is correct, but if I were going to drape some words around that fact, I might say that when we do large N holography and look at sort of kind of a bulk gravity solution where we change boundary conditions in order to match the deforming operator, in some sense, we're doing semi-classics. So the Hagedorn density of states being a purely quantum phenomenon might not necessarily be visible from this sort of holographic correspondence. Those are the sorts of words I would drape around this.
The Hagedorn is visible at large N, right? And the planar limit, large N limit, and so on in the CFD. Hence, in the bulk semi-classic Shouldn't it be?
Visible from which sorts of observables would you want to see in the bulk? Because from the bulk perspective, it's a change in boundary conditions, which is kind of a purely classical gravity statement. It's a question about like what combination of the various expansion coefficients in the metric and the Pfefferman gram is being held fixed at infinity, right? So that's visible. I agree that this is, this is a large N statement, but it's not clear to me how one would see even kind of more coarse-grained questions from that sort of holographic picture. So for instance, you could ask a different question. How do you see that the momentum is quantized if the CFT is on a cylinder, for instance? Now, from the bulk perspective, the dual to, say, a CFT state with some energy and linear momentum is a BTC black hole with M and J. So you wouldn't even be able to see necessarily that J is quantized in units of some 1 over R. So it's not crazy that some quantum properties like that quantization or the Hagedorn spectrum might not be visible from modified boundary conditions. That's what I would say, but you should take this with a grain of salt. But good, yes, other questions? If you couldn't tell from the previous talk, I like lots of questions and discussion, so please interrupt. Okay, there's nothing else I'll go on. So good, okay, so first the construction and some motivation, and then I'll show you some nice solutions to differential equations, which is some nice recreational mathematics. Good, so as I said, the motivation is now to look for a marginal deformation. So again, as we saw in the last talk, you might begin by saying, what Lorentz scalars can I construct in the stress tensor? So in 2 dimensions, again, there's only 2. There's the trace of t and the trace of t squared. So in order to construct a marginal deformation, let's start with a CFT and ask, what should I write down if I want a marginal deformation of the CFT built from the stress tensor? Well, this is a very easy question because in a CFT, one of these invariants is 0. The trace is classically vanishing up to maybe some anomaly term if there's a curvature. So that means that the only invariant that exists in a CFT is trace t squared, which of course is bilinear in t. So the only combination you can construct which would be marginal, at least classically marginal, would be the square root of that one non-vanishing combination, root t alpha beta, which again around a CFT looks like the square root of the TT bar operator. So for a CFT, there's really nothing you could do. This is the only combination that you could write down that's a marginal stress tensor flow. Great. Now, the non-trivial question you ask is, well, okay, that's fine for a CFT. What would you like to do if the C theory is not a CFT? So there are now 2 trace invariants that you have to combine in some way in order to get a marginal flow. And I'm not sure which principles to use a priori in order to choose one. So I will stipulate something. I'll say I'd like the following statement to be true. I would like it to be true that if I solve the flow equation, d Lagrangian d lambda equals my operator, my marginal operator, I first solve that flow, and then I deform that theory by TT bar. That gives me some doubly deformed theory, a 2-parameter family. I will demand that the result of that procedure is the same as first deforming my TT bar and then by my putative marginal operator, the candidate marginal operator I'd like to write down. So that's an assumption I'm going to make. Pictorially, what I mean by that is that if you start with your L0, first deform by what I'm calling R, so cal R will be the marginal guy, so that gives me some L of mu, and then deform the L of mu by TT bar, that's the same as going in the other order. And just a word for notation, I will try to always use the character lambda for the irrelevant deformation, the TT bar, and I'll try to use mu for always the marginal deformation for the root TT. Now, in particular, when I get to holography, this will be confusing because mu is never a space-time index, which is why I'm using alpha and beta instead of mu nu. So mu is always a marginal deformation parameter, not a space-time index. Okay, great. Well, I claim that if we want this to be true, that you have commuting flows, then this assumption fixes the marginal operator, our R, up to normalization. So when the trace is 0, it has to reduce to something proportional to T alpha beta, as we saw. And I'm going to normalize with an overall factor of 1/2. And the only other possibility that makes this commute for 2 dimensions is to subtract off this combination of the trace squared. And the reason why I've chosen this particular normalization with the 1/2 and the -1/4 is that this can now be written as the square root of minus the determinant of T alpha beta, lowercase t alpha beta, where that is now this traceless part of the stress tensor, which I also alluded to in the previous talk. So this is a somewhat nice simple form because as you may know, the 2-dimensional TT bar operator can also be written in terms of the determinant of capital T, the full stress tensor. So my marginal deformation I'm proposing here will be written in terms of the determinant of the traceless part of the stress tensor, which kind of looks somewhat nice. Okay, so that's the reason to choose this particular combination, the motivation of the operator. Next, I'll show you some solutions.
This diagram is computed in the classical theory.
Yes, in the classical theory, if you solve, this is purely a statement about solving differential equations. So if you solve this flow and solve this flow and this flow, the two will agree. That's right. I'll show you explicitly in a moment an example with bosons.
You won't include any RG effect or anything.
No, none of that. This is just a classical flow statement. That's right. Good. Other questions?
I mean, Lagrangian level is also classical Lagrangian commuting, like the resulting. I mean, yeah, these two different deformations, the resulting classical Lagrangian also agree, and all the spectrum.
Well, I'm not sure about the spectrum. Right. Yes, but at the level of solving flow equations for the Lagrangian with a seed theory that is, start with L0, get this L mu, and then plug that into the TT bar flow with that seed to get some result, then that agrees. So it's not clear to me that that means the spectrum agrees, right? Because we haven't defined root TT bar quantum mechanically yet. But that's a good question. Good. Other questions on this before some examples?
Why is this a good criterion to impose?
Yeah, it's not clear. So the motivation for us in particular, I'll mention later on, is that there's an analog of this class of flows for four-dimensional gauge theories, which I'll tell you about. So you can ask a very different, maybe you've heard of this ModMax. You could ask a very different question, which is there any other four-dimensional theory of an abelian gauge field besides the Maxwell Lagrangian, which is both conformally invariant and has electric magnetic duality? And the answer is yes. There's a one-parameter family called the modified Maxwell Lagrangians. And for that class of theories, you can both turn on the parameter that gives you the modified Maxwell Lagrangian, and you can turn on the parameter that takes you from Maxwell to Born-Infeld, right? The theory on a brane. So there's actually a two-parameter family of four-dimensional gauge theories, this ModMax Born-Infeld collection of theories. And that collection of theories also satisfies a commuting flow of exactly this form. So if you start with Maxwell and turn on TT bar, you get Born-Infeld. If you start with Maxwell and turn on root TT bar, you get ModMax. And if you then do a second flow in either direction, the two agree. So part of our motivation for defining the two-dimensional flow is to impose a similar criterion. But I mean, if you don't find the four-dimensional case interesting, then you could view this just as some a priori assumption that I'm going to put in and say, well, this will fix some particular combination. Right? It's I'm not sure if it's especially well physically motivated, but it's a nice property which has the advantage that it uniquely singles out one combination.
Did you say that the commutativity of the diagram is at the classical level?
That's right. Yeah. So this is.
I mean, what if I rely on the rather than the Lagrangian classical things, add some quantum effective action, and then try to do that one? Then what is the thing that does not allow me to extend this one to this one?
Good. So the issue is that essentially that I don't know how to define an analog of this operator quantum mechanically. So this involves some square root, and it's not clear to me how to find an operator that corresponds to this classical combination of stress tensors. Unlike the regular TT bar, which does have the property that it's always a well-defined local operator in the spectrum. So I'm not sure how to get quantum effective actions corresponding to this diagram because of that obstruction.
And I have one more question. Yesterday, Luis talked about the single trace TT bar deformation. So do you have any single trace version of the square, like a summation over the I should be inside of square root or outside of square root?
Yeah, good. So this will be entirely the analog of double trace. So this is like a root double trace TT bar. And we'll see holographically that it does look very similar to the double trace version of TT bar in that it modifies the boundary conditions. So then you can ask, what should you do if you want to define a single trace version of this? And that's less clear. So you might think that the single trace version of root TT bar should also be a should also correspond holographically to some supergravity solution of the form that Lewis told us about on something that looked like, say, ADS3 cross S3 cross T4, which maybe also changes the asymptotics in such a way that it could perhaps turn on a dilaton and some flux, but in a way that only depends on a marginal parameter. And that seems difficult. I don't know of any such solution. I'm not sure how one would do that. Maybe such a solution exists, but I'm not sure what it is. Very good question. Okay, other thoughts? Yeah.
Why do you expect to modify the asymptotics?
What do I expect to modify it, or what?
Why? Yeah.
Oh, why do I expect it? Just by an analogy with the single trace version of the regular TT bar.
But this one's supposed to be marginal.
That's right. Yeah, but I mean, it does have the property that this double trace version of root TT bar corresponds to just a change in the boundary conditions. But oh, sorry, were you asking about the single trace or the double trace? Okay, good. Yeah, I mean, there I don't have a good physical reason to expect. I'm purely just pattern matching with the regular TT bar, where the single trace and double trace either kind of give mixed boundary conditions but don't change the asymptotics to linear dilaton, or do change the asymptotics. And I'm naively expecting that the square root TT bar, since we know, as I'll explain later, that for this double trace version, it also gives you mixed boundary conditions, I would naively expect that the single trace version would do something analogous to the single trace TT bar, where it's not just giving you mixed boundary conditions, but it's changing the asymptotics in some way. But that might not be true because it's marginal. So I could very easily be wrong. Good. Any other questions? I think I'm doing good on time. All right, well, if there's no other questions, then I should show some examples. So this is, again, all motivated by, as we saw in the previous talk, that one clue that the regular TT bar is interesting is that you can solve the classical flow equation for the Lagrangian and get some interesting theory. So you might now ask, if you play the same game with this operator that you've just written down, this root TT bar deformation, what do you get for the deformed Lagrangian for, say, some class of seed theories? So I'll show you that. For concreteness, we're going to think about a theory of n bosons, phi I. So you can think of this as some kind of worldsheet theory or something like that, that has a target space metric capital G. In fact, it doesn't matter at all what capital G is, but there's a target space metric capital G. And I'll define this combination of derivatives of the scalars phi I and phi j contracted against the metric as x alpha beta. So the trace of x alpha beta is just the usual kinetic term. It's the target space metric contracted against d phi d phi. And again, as I've said several times, since this is a 2x2 matrix, there's only one other Lorentz scalar that you can construct out of this 2x2 matrix, which is the trace of its square. So I'll call these two combinations lowercase x1 and lowercase x2. So any theory of n bosons that is only derivatively coupled through this combination, which is a quite broad class because we usually restrict to theories with only one derivative per field. So any theory that depends on only this combination can only depend on the scalars x1 and x2. But in fact, I'll be slightly more general than that. I'm going to include a seed Lagrangian that can depend not only on x1 and x2, but on something which I schematically call x0. X0 means any other term in the Lagrangian that does not have explicit metric, by metric I mean worldsheet metric, not target space metric. No other explicit worldsheet metric contractions besides possibly the measure. So examples of an x0 term would be a potential, a v of phi, since the potential term only couples to the worldsheet metric through the measure. There's a root at g times v of phi. Or it could be, say, a topological B field coupling, say an epsilon B d phi. That depends on the metric neither explicitly nor through the measure. So that's also an example of an x0. So I'll show you on the next slide, but surprisingly, for any theory of this very broad class that depends on x1, x2, and any such x0, we can explicitly solve the flow equation for root TT bar in closed form. So let me show you that. It's actually quite nice. So for any such seed theory, all you do is explicitly compute the Hilbert stress tensor. So you vary with respect to the metric to get T, and then you plug that into the recipe, the formula I gave for the root TT bar operator with the T alpha beta contractions. And you get this kind of nice looking expression for the root TT bar operator. So it has a square root in front, but besides that, it's kind of linear in L. It just has these partial derivatives of L with respect to x1 and x2. And notice that L never appears undifferentiated. So there's no bare L without any derivatives appearing in this operator. So this is unlike the regular TT bar deformation. So if you TT bar deform a theory with the potential will get modified in some horrible way because the flow equation also depends on L. Root TT bar does not have this property. So in fact, if you root TT bar deform a theory with the potential does not change at all. It just stays the same V of phi without any modification. But if there are these kinetic terms, dependence on x1 or x2, then the flow equation will change the Lagrangian, although it does it in a very simple way. So my claim is that this flow equation, now I'm using again, mu is the derivative with respect to the root TT bar flow parameter. So my differential equation dl d mu equals r, where I'm putting a mu superscript to remind us that the expression for r can now depend on mu, because the Lagrangian will be a function of mu. There's a closed form solution, which is very simple. You can solve this by the method of characteristics. All you do is say, I'm going to define these deformed quantities, x1 mu and x2 mu, that depend on x1 and x2 with some Gaussian cinch. So notice that when you take mu to 0, so that you go back to the undeformed theory, the x1 mu and x2 mu reduce to the regular x1 and x2, so they go back to the old things. But for finite mu, they have some weird mixing, some combination that mixes into the other x1 and x2. So once you've defined these quantities, you can straightforwardly show that the solution to this flow equation is very simple. All you do is take the undeformed Lagrangian, so you take the starting theory at mu equals 0, and plug in everywhere you see dependence on x1, you simply plug in this new expression x1 mu. And similarly, everywhere you see an x2, you plug in dependence on this deformed expression x2 mu. And then that's it. You replace those, and then that will solve the flow equation. So it's a very simple.
This x1, x2 in terms of pi, some deformed pi.
Deformed pi, you said? Sorry.
Scalar field to start with.
Oh, I see. So you say, can I do a field redefinition and then express these in terms of that? That's a good question. I would think not. I'll tell you why. It's not clear from this expression whether this deformation would correspond to a field redefinition, but something which I will not discuss in this talk, but we'll hear about on Thursday, is the root TT bar deformation of integrable models. And in that case, the lax connection changes in a fairly non-trivial way. So if it was possible to express these in terms of a field redefinition, then I would think that that's not really a physical change, right? It's simply a choice of field basis. And in that case, I would suspect the lax connections not to change in a very complicated way. So my suspicion would be that this is not simply a field redefinition to some deformed field phi, but it's a genuine physical difference. That would be my suspicion.
Also, inside of square root, is it always positive or could be in some case negative?
Oh, good. Yeah. So I haven't shown it here, but we show in the original paper that the combinations under the square root will always be a fixed sign. So they can hit 0 in the special case. Sorry, no, that's not true. No, sorry, it's fixed sign even in the case if you reduce to one scalar. So if you reduce to, that's sort of the edge case, the closest you could get to it potentially swapping sign. The most dangerous case is if there's only a single scalar. But in that case, it collapses to x1 squared is the same as x2. So you have 2x2 minus x2, which is the same as x2. And x2 in that case is the same as x1 squared. So in that case, the square root collapses and the whole thing is proportional to just x1, the square root of x1 squared. And you find that in that case, it's just rescaling the kinetic term. So for the case of one scalar, this is simply a rescaling of the kinetic term. For multiple scalars, it's further away from that case, and the combination under the root will be positive. So you don't have any choice of the branch or any sign issues under the root.
Is it some physical condition that the square root inside the square root is positive, or just mathematically, if you plug in the expression, you can show that
Yeah, it ends up just being a mathematical fact. So I mean, it's related to the fact that the thing we're deforming by can be written as kind of some kind of root minus det of this traceless part of the stress tensor, which will have some positivity properties. So I don't have a physical interpretation for that. It's a mathematical fact that comes out when you plug in the quantities, I think. Good. Other questions?
Do you have a geometrical interpretation of this deformation?
Well, that's a very good question. So I do not. There was some recent work by two Chilean physicists who proposed a sort of field-dependent metric which would implement this deformation, kind of analogous to the field-dependent change of coordinates for TT bar, except in that case it isn't just a change of coordinates. It's an honestly different field-dependent metric that also has some curvature. So that's one possible geometric interpretation of this deformation. Another way you might think about it geometrically is through the holographic picture with the modified boundary conditions. So that looks somewhat similar insofar as the modified boundary conditions in holography look kind of like putting the theory on a field-dependent metric, because the boundary metric will now mix with the boundary stress tensor in some way. So they're kind of related perspectives, I think.
So what I had in mind that if you have just one scalar, then this is basically changing the compactification radius.
That's exactly right. For one scalar, it's just changing the target space radius because it's a rescaling of the kinetic term. That's right.
So what if you have more scalars or some sigma models? So that was the question.
Yeah, if you have more scalars, well, first of all, it's no longer trivial. It's not just a rescaling of the kinetic term. I guess what you're asking is there a target space geometry perspective for the case of multiple scalars? That I'm less sure of. So the answer I just gave you was really a world sheet geometry perspective, where it's saying now it's a world sheet field dependent metric. I have not thought about the case of a target space geometry interpretation, but that could also be interesting. It may be if there's n scalars that this corresponds to some, say n scalars on a torus Tn or something like that. Since in the case of one scalar, it's kind of changing the radius. You might think that this is some more complicated deformation that changes both the volume and some of the complex structure moduli of the target space torus in some way, potentially, but I haven't thought about that.
Thank you.
Other questions? Okay. All right, next we'll go on. So I showed you the general formula. Let's look at a specific example to get some intuition. So let's just start with a seed theory of n free bosons, trivial target space metric, no potential or anything like that. So L0 takes this form. The deformed theory, just applying our recipe from before, we're replacing the x1 with the x1 mu, which is this combination. So the deformed theory that we get looks like this. It's again the cosh and the sinh. Or if we plug in the explicit expressions for x1 and x2, it looks like this sort of funny combination where you have the ordinary kinetic term and then the second modified term multiplying the sinh that is some funny combination of a square root of 4 field interactions. So this looks kind of strange, but as I alluded to before, this is related to the 4-dimensional modified Maxwell theory, this ModMax theory. As I said before, this is the unique one-parameter family of 4-dimensional gauge theories for an abelian gauge field that are both conformally invariant and electric magnetic duality invariant. Looks like this. And as Roberto and collaborators showed recently, if you dimensionally reduce this action, it sort of matches this action that you would get from a TT bar flow.
May I have a question here?
Yes.
Is the ModMax theory also conformal invariant at quantum level?
That I don't know. As far as I know, the ModMax theory in 4 dimensions has not been quantized. So it's only known that it's classically conformally invariant.
Mm-hmm. And the fact that there's a similarity between this root TT bar deformation and the ModMax, is it a coincidence or there are some deeper reasons?
That's not clear to me. So part of our motivation for trying to understand this is that if one wanted to understand quantization of ModMax or ModMax-like theories, you might want to first do it in a simpler context. Instead of 4D gauge theory, do it in the context of a 2-dimensional field theory, or in particular, a 2-dimensional CFT where you have additional structure. And that might be a nice playground to start to try to quantize these funny, square root type theories. So from our perspective, we kind of want to understand ModMax type theories, and this is a toy model for them. But I don't know if there's a deeper connection between this class of 2D theories and this class of 4D theories. There may or may not be a deeper connection because both of them kind of admit a 2-parameter family of commuting flows, the sort of ModMax and ModMax-Born-Infeld theories that I mentioned before. So it may well be that there's a deeper connection that's not yet understood. So for instance, it would be very nice to understand, is there a brane or string theory type interpretation of these classes of theories? So for instance, can you engineer in string theory some deformation of a brane with the property that rather than the Born-Infeld action on the brane, you now have either the ModMax or the combined ModMax Born-Infeld action on the brane. That would be very interesting. And if that were true, then there might be a deeper connection, because you would expect that if you could do that for Born-Infeld, you should also be able to do it for DDI, for scalars in Born-Infeld. And then you might indeed expect that there's some connection between these. It might be that this class of theories is the scalar sector of some perturbed family of brane actions, and the ModMax theory is kind of the gauge sector of that perturbed theory of brane actions. That's just a very speculative hope. That might be true, and I would be very happy if that were true, and that would be a nice deep connection between these theories, but I don't know if there is such a thing.
Mm-hmm. Thanks.
Other questions? Okay. All right, I have about 10 minutes left to tell you about the last part. So there's this holographic interpretation, which I mentioned, so which I'll briefly sketch and then tell you about some future directions. So now we're turning to ADS3 CFT2. And again, as we heard about yesterday in Lewis's talk, we have the general expectation that if you deform a boundary CFT by some double trace or more generally some multi-trace operator, that this should correspond, at least from the perspective of large N and low-lying operators, this will correspond to some change in boundary conditions for the bulk field, like the bulk metric. Let's quickly remind ourselves of how we see that in the ordinary holographic dictionary. What you would do is start with your bulk gravity action that has both an Einstein-Hilbert term and the appropriate boundary term, and you would vary it and put it on shell. And you would find that the variation of the action on shell can be written as a boundary term that looks like a contraction of a T alpha beta, which would have some explicit expression in terms of the Pfefferman-Graham extension of the metric, times this delta gamma, where gamma is now the boundary metric. And you would look at this and interpret this by saying, so now gamma alpha beta is somehow the source. This is the boundary metric. It's a source for a dual operator, and the stress tensor T alpha beta appearing in this expression is the dual operator in the field theory. In particular, it's the expectation value of the dual operator in the field theory, in the usual holographic dictionary. And then you would say, well, okay, for a well-defined variational principle, the variation of the action on shell should vanish, including the boundary term. So we have to demand that delta gamma alpha beta vanishes. And that's the usual Dirichlet boundary conditions for the metric. So that's with no deformation. Then you could say, well, I'd now like to deform this story by adding some operator to the CFT. So you take the boundary action and send S to S plus delta S, where now again, mu is the deformation parameter, not the spacetime index. So we deform by some integral of some, in this slide, I'll do the double trace case. So in this case, we assume O mu is double trace, which means it's the square of the operator, which is dual to some fundamental field in the gravity theory, for instance, the metric. And for this class of deformations, there's a particularly simple result. So we have to remember that in the holographic dictionary, there's a correspondence between the action of the dual field theory. That's this SQFT. Now that corresponds to really the generating functional for connected correlators in the bulk, which we identify as the bulk gravitational action. So there's not quite a one-to-one correspondence. There's actually, for the case of double trace operators, there's a relative sign. So what I mean by this is that if you deform the boundary QFT, or in this case CFT for the C, by some operator, then the change in the bulk on-shell action will be the same up to a minus sign. This is true for double trace deformations, that the two agree up to a minus sign. So once we know that, you could say, well, I would now like to deform my boundary theory, but interpret that as simply modifying my choice of metric and stress tensor in the bulk. So by that, I mean, what you would like to do is look at this equation and then take a derivative of both sides with respect to mu to get something like this down here. So you say the mu derivative of the variation of the action should be the mu derivative of this combination over here, which is my delta S mu. And if you take those mu derivatives, you now get some differential equation that involves variations and mu derivatives of the metric and stress tensor. So you can solve that differential equation in good examples. In practical examples, you can find a solution for a gamma of mu and a T of mu with the property that this combination is the solution for delta S of mu. And that's very nice, because if you can find such a solution, then that means that the deformed action, or precisely the the variation of the deformed on-shell action takes exactly the same form as the undeformed case, which again looked like this, up to simply replacing the T and gamma with mu-dependent quantities. So then you're in luck, because then that means that all you've done is changed your metric and stress tensor in some mu-dependent way. And now to have Dirichlet boundary conditions for those modified metric and stress tensor, you just hold this new delta gamma fixed. So I'll give you an explicit example of that for the regular TT bar. So this is known. This is some work by Monica Guica and Ruben Montan. So in that case, if you TT bar deform the boundary theory, you can find an explicit expression for the metric, and in this case, the trace reverse stress tensor. It's just easier to write the solution in terms of the trace reverse T. So it's T alpha beta minus the trace. But in terms of that T hat, you can solve that differential equation exactly, and this tells you what the mixed boundary condition should be at infinity. So for the regular TT bar, everything works very nicely. So the interpretation of the regular TT bar is that adding TT bar to the boundary theory corresponds to a new variational principle where you hold fixed not the usual metric, but this funny lambda dependent metric that now depends on the undeformed stress tensor in some way. And as we heard yesterday, that can be interpreted through the negative sign as some Dirichlet boundary conditions on a finite cutoff surface. Okay, what about for the root TT bar? So in that case, things are slightly different. So we have to remind ourselves, how does this entire story work, not just for double trace deformations, but for more general multi-trace deformations? So a general function of some operator O. Now, in that case, this was worked out many years ago in a paper 2007. The generating functional, which again is supposed to be identified with the bulk gravitational action, is modified by a funny combination that looks like, f, the function f evaluated on this dummy variable h that will set to some particular value at the end. But it looks like f minus h f prime. Now you can schematically see that if f goes like h squared, this is like h squared minus 2h squared, so it's minus h squared, which reproduces what I told you a couple slides ago, that in that case, the two differ only by a minus sign, right? You deform the action and you deform the boundary, the bulk action just by the same thing with a minus sign. But something funny happens for the case of our root TT bar case, because here, the schematic form of the function that we're deforming by is a square root of a double trace combination. And in that case, if you evaluate this combination of derivatives, it vanishes. So the claim is that for the root TT bar deformation, the change in the generating functional of connected correlators, or equivalently the bulk gravitational action, should be 0, not just minus of the boundary deformation. So that's kind of funny, but we can actually find explicit boundary conditions which do that. So I'll show you the solution, and then I'll conclude. So this is the answer. The change in boundary conditions which have that property, that they leave the sort of variation of the bulk on-shell action, which looks like this T delta gamma, is left unchanged. So it's the same in both the mu-dependent and the mu-independent undeformed variables. The solution which does that is this. So just as in the TT bar case, when we were holding fixed a combination of the undeformed metric and stress tensor, now we hold fixed this combination, gamma mu alpha beta, which looks like this strange combination of a cosh times the undeformed metric and a sinh times the undeformed traceless part of the stress tensor. So again, this lowercase t is the traceless part. And again, r is the usual root TT bar operator, which appears in the denominator. So this is the holographic interpretation, which is it's somewhat satisfying that the coshes and sinches appear in sort of the same way as it does for the scalar theories or something. But there are many nice properties. This is work in progress that should appear with some other collaborators, but there's many nice properties of this change in boundary conditions. So for instance, in the same way as the flow equations for the Lagrangian commuted, as we said before, there's also a commutativity property for these boundary conditions. So if you start with some metric and then plug in these changed boundary conditions, and then go back to TT bar and plug in the root TT deformed boundary conditions as a seed into here, that's the same as going in the other order. So holographically, things seem to commute as well. There's some other properties about that I can tell you about afterwards if you like, you can ask. But I'm just about out of time, so let me just summarize and explain some of the many open questions about this. So what I've told you today is about a new marginal deformation called root TT bar. I showed you the solution for deforming a theory of n bosons, which gives a fairly nice differential equation that's related to the 4D ModMax. I told you about this commutativity property, which is another nice feature. You should come to Alessandro's talk on Thursday at this conference, where he's going to tell you about the integrability properties of this root TT bar deformation. And I told you about holography. And although I didn't mention it too much in this talk, I mentioned in the informal talk that taking flow equations involving both the TT and the root TT can be used to engineer many types of actions in higher dimensions, like these Namagoto type actions and also string actions, brain actions, which is based on some other work in progress. So for that reason, I think this class of deformations is interesting and involves some nice new ideas and probably deserves closer study. But for some future directions, the most obvious question, as many of you have asked me about, is how to define this at the quantum level. And I'm not sure how to do that, but part of the reason for studying integrable models is that that might give a nice place to start. And just a quick assortment of some other questions you might ask is whether this can be supersymmetrized, just as TT bar can, and whether you can find flow equations for other observables like the S matrix or torus partition function, which I was also asked about here. Or whether you can understand it as coupling to some kind of gravity. So I think there's a lot to do. You can ask many of the same questions that people have already answered for TT bar in the root PT context, and I think there's some hope that there's interesting things to learn and that this might teach us some nice facts about two-dimensional QFTs and maybe even higher dimensional theories. So with that, let me conclude, and I'm happy to answer any questions.
Okay, thank you, Christian. Any questions for our speaker? Please go ahead.
The number 3 is, are you having in mind like a two-dimensional space equal to the 2D gravity or something else?
Yes, so I'm thinking in particular something analogous to John Cardy's work where TT bar can be thought of as sort of, if you Hubbard-Stratanovich the TT bar combination, it looks like coupling to some random metric, some H. We thought a little bit about this, whether one could do the same thing with root TT bar, because you would have to kind of analogous to the question I received in the informal talk. You can imagine adding a Hubbard-Stratanovich field with a square in order to reproduce the root TT bar when you integrate it out. There are some subtleties with this that we still don't understand, because it seems that in order to run a similar argument with root TT bar, it appears that you need 2 fields. You need a Hubbard-Stratanovich field and then a scalar. And it's not totally clear to me how one should interpret that, but it might be the case that the analog of John Cardy's work for root TT bar might be coupling to some kind of random dilettante gravity, which I think would be interesting. But that's extremely speculative. I don't know if that story makes sense yet, but it would be nice to understand. Other questions? Yeah.
Yeah. So it seems to me that this user TT bar information is interesting because it maintains integrability and so on. But in your work, you don't care about that, right? So you are not dealing with the TT bar information with some integral model.
So I haven't mentioned that there's a separate talk on Thursday. That
Okay. Yeah. So if you don't care about integrability, then why not consider, for example, third root of TT bar?
Right. Yeah. So you can take random combinations of TT bar.
So what's the real advantage of this non-local information?
Right. Yes. Well, I mean, as it turns out, this does preserve integrability. So that's one piece of motivation. You can ask, is there any marginal deformation in 2 dimensions which preserves integrability for, say,
but not all of them, right? Only some special set of the integral models can be preserved, I guess.
That's right. For a fairly large class, I mean, principal chiral model with Wess-Amino term for nonlinear sigma models on various target spaces, kind of semi-symmetric spaces and symmetric coset models.
So even that is also classical level.
That's right. This is just a classical lax connection. That's right. But no, I agree. So it's somewhat more speculative work. It's certainly not on as firm a footing as TT bar. So I'm mostly just trying to argue that it's not immediately crazy and it's worthy of further study. But the pieces of evidence I think that we have is the maintaining integrability in that class of examples, the commuting with TT bar, the connection with ModMax theories that are of independent interest to another community, and the holographic interpretation seems that there's a tractable modification of the boundary conditions. So there are at least hints that this deformation might make sense and isn't just some random combination of T's that you could add. But I agree, it certainly requires more investigation to be put on firm footing. Good. Other questions? Yeah.
So you said that here the potential of the Lagrangian is not modified.
That's right.
right? And is that because you're deforming by square root of the determinant of the traceless stress tensor instead of the standard stress tensor? Right?
That's one way to interpret it, right? You could say that because it's the traceless part of the stress tensor, that is the combination for which the potential drops out, right? So that it's not affected.
So have you considered doing just instead of root of determinant of the traceless stress tensor, just determinant of the traceless stress tensor?
Oh, just the determinant, not the root.
Does that lead to something interesting?
But that's a good question. So that would, I guess it would be like, it would still be irrelevant. It's like the usual TT bar, but it's using a different combination.
Right. Like maybe like the factorizability will not work anymore, and right, and the operator probably it's not finite because to make it finite you need a particular combination that appears in TT bar.
That's right.
But you can still get some Lagrangian whose kinetic term will be modified, right? The potential will still be unmodified.
That's right. So that would indeed give a different class of classical flow equations for the Lagrangian that might be interesting. Certainly would not make sense quantum mechanically because TT bar is the only combination for which it drops out. But indeed, there could be something interesting. I haven't thought about that, but yeah, that would definitely leave the potential unchanged.
So if okay. So if in that case it doesn't make sense quantum mechanically, do you think in this case it will make sense quantum mechanically, like with
for this operator?
Yeah, with the square root.
Yeah, I think, so I mentioned this a little bit in the previous talk, but I think that this operator will not make sense universally quantum mechanically, but maybe for some class of theories, you might be able to define this operator in the spectrum. So for instance, for a free fermion or for the Ising model or something, I think that this operator will not be there in the spectrum because it's believed that these are isolated points and there are no marginal deformations of, say, Ising besides disorder. But for the boson case, it seems like there might be some chance of showing that there is a quantum operator that corresponds to this root TT. So I think in order to do that, one should not attempt to use a Zamolodchikov type argument, which is universal and applies to any field theory. You would have to put in additional assumptions. Yes.
So I have a question about the ADS3 CFP2. I think in the usual TT bar deformation, I think three-dimensional Einstein equations are related to trace relation with TT bar deformation. So is there a similar connection between three-dimensional Einstein equations and the root of TT bar deformation?
Sorry, connection between 3D Einstein.
Three-dimensional Einstein equation and root of TT bar. I think in the usual TT bar deformation, there is a relation between three-dimensional Einstein equation.
You mean the trace flow?
Yeah, trace relation with TT bar deformation.
Oh, I see. Yeah. So here it's kind of funny. I mean, so for instance, with the cutoff ADS for TT bar, you can derive the trace flow equation from the gravity side. Here, the analogous trace flow equation would be very simple. It would be trace equals 0, right? So you can actually, I mean, it's a trivial exercise, but you can derive that with the modified boundary conditions I wrote down, which for some reason I'm not advancing. Sorry. Yeah. Oh, there we go. That was probably my fault. Yeah. So this is a very simple exercise, but with these modified boundary conditions, you can simply plug in. So if you take the trace of, so first you compute the traceless parts of the deformed stress tensor T, and then you add back in the trace so that you get the deformed capital T. So that gives you kind of the deformed stress tensor using root TT bar. And you can convince yourself that the trace of that deformed stress tensor with respect to the deformed metric remains 0. So it's not as interesting as the trace flow equation for the regular TT bar, where it's kind of like, you know, trace T is -2 lambda TT bar or something like that, which is a sort of equivalent definition of the deformation. Here, it's just simply the statement that the trace stays 0. Right? Good.
Any questions from our online participants?